Okay, so welcome back to another video. So we got another interesting problem to solve here. So the following question is, we're being asked to prove that gamma, lowercase gamma, is equal to the negative integral from 0 to infinity of ln of x divided by e to the x dx, where, from the definition, lowercase gamma is defined as the limit as n approaches infinity of the difference of the harmonic series. So the summation from n is equal to 1 to n of 1 over k, and then minus ln of n. This lowercase gamma is an interesting notion, because this is actually known as the Euler-Mascheroni constant, which is a constant that's recurring in analysis and number theory, and it's also made its appearances in the following, such as it can be used in expressions involving exponential integrals, the Laplace transform of the natural logarithm, calculations of the digamma function, the product formula for the gamma function. It's even used for the first terms of the Laurent series expansion for the Riemann zeta function, and it goes on. The list goes on as well. I'm also reading this through Wikipedia of some of the appearances this constant has made itself in. So now that we got that out of the way, now you know what Euler-Mascheroni constant is. So the whole point of this is we're trying to show that this equation here is equal to this integral. So let's get started. Let's actually define the following. So we know, and I've said this several times from past videos, that the constant e, and we're gonna define this as Euler's constant by using the definition with the limit as n approaches 0 of 1 plus n raised to the 1 over n. Okay, so that's Euler's constant. So now, why don't we actually take the power of x, and so that way we can manipulate that. So I'm just going to imply with that. So we have e to the x is equal to, so x is a power, so I can just multiply the power into here. So this would be the same argument as follows, of 1 plus n, and then this is just x divided by n, this power. Okay, so now let's actually do a substitution. So I'm going to let u equals x divided by n. So then also don't forget, since there's also a term of n right here, so I also want to do the substitution for n as well. So when I do the multiplication, I get nu equals x, and then divided by u. So that means n is equal to x divided by u. Okay. Now also notice when n approaches 0, so when n is 0 here, so that means u has to approach infinity. So as n approaches 0, then this implies that u approaches infinity. So with that, we can rewrite our new limit in terms of u. So I can rewrite this in terms of u. So this is equals the limit as u approaches infinity. Let me rewrite this infinity. U approaches infinity of 1 plus, let's see, so n is equal to x over u, so that, and then raised to the u. Okay, nice. And this is for x, for some real number x. Okay, let me just establish that as well. Okay, so with that, now let's also say, because we have that ln of x divided by e to the x, which in other words, we can also rewrite this in just under using our rules of exponents. We can actually rewrite this, so this is the negative power, so e to the negative x. So using our same definition in terms of e and e to the x, we can just multiply the negative x for the power and then distribute. So the same thing applies. So this would also have to say e to the negative x is equal to the limit as u approaches infinity of 1 minus x divided by u, and then raised to the u. Okay, now that we have this, we established our rules for the Euler's constant with the definition. So what we want to do now is, because we want to make a change of integrals, what we're going to do afterwards, well, in order to make that change of integrals rather, we're actually going to subtract the degree of our function e to the negative x by 1. So in other words, we're subtracting our power u, so we have our new power is u minus 1. So it doesn't necessarily mean that it's equal to e to the negative x, but rather it's congruent when we take its limit. So in other words, the congruent symbol is just 3 horizontal bars. So that means it's the limit as u approaches infinity of 1 minus x over u, and then u minus 1. Okay, nice. So now that we have that, so let's define the function. Now let's define our integral. Let's just, for now, we're just gonna ignore the negative symbol, and let's just focus on just the integral itself. We're just ignoring the negative constant for now. So let me just define the function, not the function, our integral to be I equals this positive integral. So this is from 0 to infinity of ln of x divided by e to the x dx. Use my chair for this. And then in other words, I can, just like before, I can just rewrite the e to the x in terms with using our rules of exponents. So now we're ending up with a negative power, so this is equivalent to e to the negative x ln of x dx. And it's a good thing we did this, because we can actually substitute our Euler's constant definition of e to the negative x with this, and with the limit as u approaches infinity of 1 minus x over u, and then u minus 1. Now we're actually going to take the limit in terms of n, so we're just substituting everything we have in terms of u just for n. So this is the limit as n approaches infinity of the integral from 0 to n, because we have that n is infinity, so we're just going to replace this with n, and then multiply that with our substitution. So this is 1 minus x divided by n with the power of n minus 1, then multiply our ln of x dx. And now we're actually going to be doing yet another substitution, in this case a U-substitution, or let's actually, instead I'm going to define this as t equals our inside. So let t equals 1 minus x divided by n. Okay, so that means dt is equal to, so n is just a constant, so this is equal to -1 divided by n dx. And then I want to multiply the negative n to both sides, so we get -n dt is equal to dx. Okay. And also there's an ln of x, so I want to do a substitution for x. So what I can do is I can actually add an x divided by n and subtract a t, so that we have x divided by n equals 1 minus t. So, and then just multiply the n, so we have that x is equal to n times 1 minus t. Okay? And don't forget that we also need to change our bounds of integration as well, since now our new integral will be in terms of t. So this means as x approaches n, So that means when we plug n for x, we get 1 minus n over n, which is or 1 minus 1, so that's 0. So this implies t approaches 0. And then as x approaches 0, so that means 1 minus 0. So that means t approaches 1. Okay, nice. And now we have our new integral, so that means when we're doing our substitution, so we have I is equal to the integral from this is the top bound, so 0, 1, and then our substitution where this is 1 minus x over n, that's t raised to the n minus 1, and then multiplied by ln, and our x is n, then multiplied by 1 minus t, then where's it, right here, negative multiplied by negative n dt. Okay, nice. So okay, so notice that 1 is supposed to be bigger than 0, so when we apply our rules for changing the order of integration, this will have to be a negative integral. But there's also a negative number with negative n, and n is a constant, so I can actually move that outside the integral, and then the signs will cancel. So that means this integral is a positive integral. So this is t, let me move the n outside first, and then right. So this means n is equal n multiplied by 0 to 1 of t to the n minus 1, and then multiplied by ln of n times 1 minus t dt. Oh, I forgot to write the limit too, but that's okay. I can just move that to the next step. So this means this is the limit as n approaches infinity of n. Here we have ln of n times 1 minus t, so we can actually use our rules of natural logs to actually split this product into two sums of natural logs. So this is n times the integral from 0 to 1 of t raised to the power of n minus 1, then multiplied by ln of n, then plus ln of 1 minus t dt. So now I can distribute the t minus 1 to both of these natural logs, and then I can actually take the and then we can split this into two integrals as well, and that would also mean I have to distribute n as well. So this means limit n approaches infinity inside, so that means n multiplied by the integral from 0 to 1 of t to the n minus, so this is ln of n, and ln of n is a constant, so I can move that outside, but I'll worry about that later. Let me just finish writing this out first. Then plus n times the integral from 0 to 1 of t to the n minus 1, then multiplied by ln of 1 minus t dt. Okay. Now, next step, like I said, ln of n is just a constant, so I'm just going to move that outside. t n minus 1, ln of 1 minus t dt. Okay, so now the next part is let's actually calculate specifically this definite integral over here. So why don't I actually calculate this with red instead? So let me see. Okay, cool. I'm actually going to write it on the side over here. So that means we have our definite integral 0 to 1 of t with the power of n minus 1 dt. So it's just power rule. So just add 1. So and then divide by that. So this is simply just 1 over n t to the n, and then evaluate it from 0 to 1. Then when we plug 1 for t, so we simply just get 1 over n, and then we plug 0, we get 0, so 1 minus 0, so therefore it's 1 over n. Okay? That's nice. So that means the limit n approaches infinity of n, and then natural log of n, then that's being multiplied by 1 over n, okay, and then plus, now we have this integral to that we need to focus on now. So what we can do is, let's focus on our natural log of 1 minus t. So because we are integrating this from 0 to 1, close the close interval, of course. So that means when t is an element between our closed intervals 0 to 1, oops, that's an ugly looking one. Okay, we can actually use our definition of our Taylor series and expand the natural log of 1 minus t as the following. So ln of 1 minus t is equal to the negative summation from k is equal to 0 and then all the way up to, or actually it's k is equal to 1. The index starts at 1, not 0. From k is equal to 1 to infinity of t raised to the power k and then divided by k. Okay, so with that, now let's actually substitute this summation back into our integral. Now this would also mean that this is a negative, so I can factor that out. So now this has become a minus n. Okay, and then multiply by our integral 0 to 1 of t to the n minus 1, multiply with our summation of, well, now we have the limit as n approaches infinity, so our upper index has to be from n, and then k is equal to 1, not 0. Keep messing that up. It's supposed to be 1, and then of t with the power k divided by k and dt. Okay, nice. We can actually use our rules of summations, meaning I can actually take out the summation and move it outside the integral, but we also have that 1 over k is a constant. So therefore, I can factor out the 1 over k and rewrite this new limit. Well, not really the new limit, but our new simplified integral. So this is the same thing. And why not? Because let's factor this out, or let's cancel the terms out. N times 1 over n, so that's just simply we're left with the natural log of n. And then minus, okay, so I can move out the summation. So this is k is equal to 1, and then n over k, and then multiply with our integral from 0 to 1 of, and then t to the k, they share the same base, so therefore I can combine the our exponents, so we get n plus k and then minus 1 dt. Okay, nice. So now we can actually calculate this definite integral, which is very simple because we're actually just using the power rule just like before. So that means the integral, the definite integral from 0 to 1 of t to the n plus k minus 1 dt. This is simply just so plus 1 and then divide by that. So this is just t to the n plus k divided by n plus k, and then from 0 to 1. Simply, when you plug 1 for t, so you just get 1 raised to the n plus k, but that'll always just be 1. So this is just 1 divided by n plus k. And then minus, when you plug t for 0, it's just going to be 0. So therefore, it's the definite integral from 0 to 1 of t to the power of n plus k minus 1 is just 1 divided by n plus k. Okay, cool. So now we can actually just substitute, oops. So now we can just substitute our evaluated definite integral with 1 over n plus k. So that means this is, rewrite the limit again, equals 1. And then this is, okay, so n over k, then multiply by 1 over n, n plus k. So this is just n divided by k times n plus k. Okay. And now the next thing I want to do now is now we want to evaluate this our series here. So what I'm actually going to do is I'm actually going to add and subtract a k, add and subtract k. So I think I got room to put this. Yeah, okay. Yeah, I got room for this. Limit n approaches infinity. This is ln of n, then minus summation and k equals 1 of now I'm actually going to group this as well. That way what we're going to do next is we're actually going to evaluate two different series. So this is n plus k minus k and then divided by k times n plus k. Okay, so with this, now we can actually split this into two series, two summations. So rewrite the limit as n approaches infinity of ln of n, then minus, so n plus k divided by n plus k, they cancel, so this is just n k equals 1 of 1 over k, and then I can just distribute the negative into here, so this will become a positive. So this is the summation, so these k's will cancel, yeah, and then we're left with 1 of 1 over n plus k. Now let's actually take the limit. Well, specifically, let's take the limit as n approaches infinity of this series. When we do that, this actually, let me write this in red again. So, focusing on this this summation here. So when n approaches infinity, then this is actually going to the series is actually equals 0. So now we're only left to focus on these two terms here. But don't forget, we also started with the negative integral from 0 to infinity of ln of x e divided by e to the x. So let's actually multiply the negative. So therefore, let me just rewrite from before that. We have the negative integral from 0 to infinity of ln of x divided by e to the x dx, which is equal to, since we just focus on evaluating the positive integral of ln of x divided by e to the x, so let's simply just multiply the negative to this limit here. So this is the negative limit as n approaches infinity of the natural log of n minus the summation n k equals 1 of 1 over k. Okay, this is by using the constant with -1, so I can actually just distribute the -1 into here, and we also have that I can also reverse our terms since this is commutative. So this is now the limit as n approaches infinity of, so this will be positive when I distribute the negative, so this means the series will come first, and k equals 1 of 1 over k, and then minus the natural log of n. Oh, so what is this? We actually have our definition of the lowercase gamma. So we have just shown that the gamma is equal to this. We just showed that lowercase gamma is equal to this, our negative integral. So we're done. So therefore I can write the conclusion again one more time. Gamma, which is defined as the Euler-Mascheroni constant, I almost said number, the proper term to say is constant, is equal to the negative integral from 0 to infinity of ln of x e to the x dx. And we are done with our proof. It's pretty neat, right?